Welcome back to my Roblox Advanced Scripting tutorial series. My name is Braldiv, and in this episode we'll be discussing about physics. And wait, Newbert, what are you doing all the way out here? Shouldn't you be focusing on your scripts and whatnot? Oh my god, he's doing it again. Okay, you know what, Newbert? You really asked for it this time. This is the last straw, and now you are going to be out of this world. Goodbye, Newbert. Welcome back. This video is going to cover physics, which allows us to create cool things like this pet follow script that I created, where it follows the player behind their back. I've even created a projectile system. If you click wherever you want the fireball to go, then it's going to go in that direction. I've also created a ragdoll system where if you reset your character, then your character is going to be a ragdoll rather than having it explode into a million pieces. I also created a little cool trampoline as well using springs. And all of this can be done using physics. Oh man, that is one powerful trampoline. But anyways, all of this can be done by using physics, and this video is going to serve as a broad overview of how you can use physics inside of your Roblox games and how we can script them so that we understand how to create cool systems like this. So with that being said, let's go ahead and go straight into the episode. Now that we understand it, let's implement physics inside Roblox Studio. But before we do, I want to give a basic definition of what physics is. And to explain, physics is essentially the science that studies how things move and interact with the world and other objects within that world. And we've been working with physics actually throughout this entire tutorial guide without us even realizing. And to show you a little example, I'm just going to hit run, and I whipped up a little script that basically creates all these parts that just rain from the sky and is now spreading all around this base plate. And Roblox's physics engine is calculating how these parts are interacting with all of these other parts within the world. And as you can see, my PC is starting to lag a little bit with all of these parts that are in here. But we've essentially worked with physics throughout this entire tutorial guide without us even realizing. And there are some specific properties that we've mostly been using that actually does involve physics. Like if I were to insert a part here, by default, anchored is turned off, and what that means is we're applying Roblox's physics to interact with the world in how it would if we were to apply physics to it. So if we were to hit test and hit run, then what's going to happen is it's just going to fall down just like this. And if we were to change its anchored property to true, then we're going to ignore Roblox's physics engine so that it's just going to stay stationary. I think we understand how this works. And there are even some other properties as well, like Roblox's gravity that we can change here. So by default, Roblox's gravity is 196, but if we change it to 0 gravity, and what's going to happen is all the parts that are inside the game are not going to be affected by gravity. So as you can see, all these parts are now in 0 gravity, and oh my goodness, it is lagging my computer like crazy. But gravity is how we can measure the objects that are inside of our world being pulled down to the game's core, I guess, if that makes sense, because that is basically what gravity is. And if we make it 0 gravity, then we are not having any gravitational pull towards the center of the world. So that is basically some properties with physics. And now what I want to cover in this episode is some of the services and objects that Roblox has provided to us to create cool systems. So Roblox's physics engine is very packed with a lot of features that we can use towards our advantage. And one of those features involve mover constraints, which are essentially objects that apply force or torque to move one or more parts in a specific direction or multiple directions. Now, I am just throwing a bunch of terms out there, so if I were to quickly explain what these concepts mean, think of assembly as like a part that allows all of its parts that are around it to be connected. And this is the part that's going to be used to apply physics to it. So since this is one part, there's only one assembly, and it's usually in the center of this part. But if we were to have a more complicated model like this Newbert model over here, this Newbert model would probably have like 15 parts in it because this is an R15 character, but it only has one assembly, which is probably somewhere right here in the center of its chest. So usually when we're working with physics, we're only working with one assembly. So that's what that means. And then there's things like applying force and applying torque. So force is essentially when you take a part and you move it alongside one direction or multiple directions. And when you apply force to it, that is what allows it to move in that direction during runtime. And then torque is kind of the same thing, but instead it applies rotational force if we were to rotate it during runtime. And that is essentially what that means. So now that we kind of understand those definitions, we can move on to applying these mover constraints so that we can move these parts however we so desire to. And the first object that I want to introduce is called linear velocity. Now, there's two ways that we can add mover constraints inside of our game. I'm just going to show you one of them for right now. What I'm going to do is go to model, and we're just going to insert a new part just like this. And within this part, what I'm going to do is hit the plus sign, and we're going to add an attachment. Now, the reason we're adding an attachment is because we want this attachment to be essentially our assembly. And we don't want the mover constraint to work on the part itself, but instead we want to work on its attachment. So what we're now going to do is insert a linear velocity. And essentially what linear velocity is, this applies force on an assembly to maintain a constant velocity, whether it's in one direction or whether it's in two directions. This is called a plane, or we can do it inside of a 3D vector where we use all three of these vectors. So what I'm going to do is rename this attachment to attachment 0 just to make things more organized. And inside this linear velocity, we need to set our attachment 0 to the attachment that we just created. So I'm just going to click on this and click on attachment 0. So now it should be activated. Now there are some properties here that we can work with, but the most important thing here is this vector velocity property. Now velocity is basically the speed at which an object moves in a certain direction. So we have three directions to work with, and if we were to work on the x direction, so if I were to set this to a number like 1,000, we can now see that there's an arrow that's going to be moving in this direction once we hit play. So if I hit test and I hit run, then what should happen is this part is just going to be zooming in the x direction using a constant velocity. So it's going to maintain the same exact speed from where it started to where it ends. And so that is basically what is going on over there, and that is how we use linear velocity. Now, angular velocity is basically the same thing, except it applies torque onto an assembly line, which basically is a way of saying that we want to constantly rotate a part in a certain direction. So what I'm going to do is disable our linear velocity, and we're going to insert an angular velocity, and I'm going to set attachment 0 to our attachment. And what we can do is make our angular velocity go 1,000 on the y direction. So it's going to sort of spin around like this. But one thing we also need to do is make sure that for our angular velocity, our max torque is set to something that's higher than our angular velocity. So we can say something like 10,000 or something, just so that we have something in place. So now if we hit run, what we should see is this part is now having a constant rotation on the y-axis. And that is basically what angular velocity does. It's like the linear velocity's counterpart, except this one works with rotation while the other one works with position. The next two mover objects I'm going to introduce are called AlignPosition and AlignOrientation. And essentially what these do is they apply force or torque to move two attachments together to kind of mirror each other and reflect on each other's position and orientation. This might make sense once I actually show you what this looks like, but basically what I'm going to do is take this part and I'm going to duplicate it and move it to the right side. And inside of this other part, what I'm going to do is delete its angular velocity and linear velocity. We don't really need them anymore. I'm going to make attachment 0 be renamed to attachment 1. And what I'm going to do with the original part's angular velocity is disable it, because now we're going to apply an aligned position to this first part, just like this. And what we're now going to do is in the attachments category, we're going to set attachment 0 to its attachment, and then attachment 1 to the other part's attachment. So now there should be a visual line right over here, just like this. And so now what we can do is if we were to hit run, then what's going to happen is this part, oh, it's kind of just sliding all around. Okay, I might need to take the second part and anchor it just like this so that it stays in place. So now if we hit run, what should happen is this first part is going to try and follow the second part's position wherever it's at, because both of these attachments are, attached to each other. So if I were to move the second part, then the first part should be following the second part because it's trying to match its position. And we can do the exact same thing with align orientation if we were to hit part on the plus sign, and if we were to insert an align orientation. Let's take attachment 0, attach it to that, attachment 1, attach it to that. So now we have an align orientation and an align position so that we can copy its position and orientation to reflect on the second part, just like this. So if I were to rotate the second part, then the first part is going to try and mimic the orientation of the second one. Now you might be thinking off the top of your head, this looks a lot like a pet following script, and you are right in how you can use align orientation and align position to make this happen. And that's actually what we're going to be showcasing right now. Okay, so I'm going to show you how you would be able to script a pet follow player script using align position and align orientation. So I just quickly whipped out this pet, and what I'm going to do is I'm going to insert 3 instances inside of this pet. The first thing is going to be our align position, the next thing is going to be our align orientation, and then finally we need an attachment for this pet as well. So I'm going to rename this to attachment 0, and for align position and align orientation, instead of using its default 2 attachment mode, we're actually going to set this to 1 attachment. And the reason we're going to use 1 attachment is because we don't need to have 2 attachments for this to work. And so to show you how we would use align position and align orientation, we essentially want to take the attachment of this pet and we want to set a goal position and a goal orientation, and we want to update that every single, let's say millisecond, or every single heartbeat if we were to use run service. We want it to be a goal of this character's, let's say, orientation to look in the exact same direction as the character. So we want this orientation to follow the player's direction. For the position, we would probably want it to be somewhere behind the character, either on the right side or the left side. So that's something that we would do, is we would just calculate the character's position orientation and sort of modify it so that the pet can follow that calculation. And so we only need 1 attachment for this to work. And I'm going to show you that when we start scripting it. So I'm going to hit the plus sign inside of pet, and we're going to insert a script. The first thing we're going to do is make reference to our pet by saying local pet equals script.parent. Then we're going to reference its align position and orientation. So we're going to say local align position equals pet.align position. And then we're going to do the same thing for align orientation equals pet.align orientation, just like this. And what we want to do is actually make reference to run service. So we're going to say local run service equals game:get service run service, just like this. And what we want to do here is say run service dot stepped connect function, open and close parentheses, enter. So we want to update the align position and align orientation every single heartbeat rather than doing it just once. So here's something that we can do. Align orientation is actually pretty easy because all we need to do is take the pet's align orientation's C-frame and just set it to be, let's say, the character's humanoid root parts position. That's literally all we need to do, and it's going to follow it. So what we're going to do is make reference to our character. And just for simplicity's sake, what I'm going to do is just going to hard code the character location. So we're going to say local character equals game.workspace : wait for child. And then this is just going to be the name of our player, which is going to be Brawl Battle. But in this case, yours is going to be different with your username. And then we're going to say local humanoid root part equals character.humanoid root part, just like that. And so what we're now going to do inside of here is update the align orientation to match the C-frame of the humanoid root part. So we're going to say align orientation.C-frame equals humanoid root part.C-frame, just like this. And this is the only line we need for align orientation. Now for the position, this one's going to be a little more tricky because essentially what we want to do is we want to match the humanoid root part's position, plus consider the humanoid root part's look vector, which is in this direction. And we want to multiply that by a scalar so that we take its look vector and we set it backwards like this, plus a right vector as well with a scalar so that it moves in this direction as well. It might make sense to you once we start scripting this, but essentially what we're going to do here is we're going to say AlignPosition.position equals, we're first going to have it match the humanoid root part position, but then what we need to do is we need to add the look vector plus a scalar. So what we're going to do is say humanoid root part.cframe.look vector. So this is going to give us a vector3 value that's going to tell us the direction of where this player is looking, which in this case, it's going to be in this direction. So we're going to multiply this by a scalar because the look vector only contains zeros and ones. So if we multiply this by a scalar, then it's going to move back 3 studs, essentially. That's like what this is saying right here. And then what we need to do is finally add a right vector as well. So we're going to say plus humanoid root part.cframe.right vector times 3. Because once again, right vector only returns a vector 3 of zeros and ones. So if we multiply it by a scalar of 3, then it's going to shift to the right by 3 ever so slightly. So that's how we calculate the position of where the pet should be. So if we now hit test and hit play, then what we should see is this pet, my character was just floating, and that's because I forgot to turn off zero gravity. So it's 196.2. That's the default gravity. So if we hit play, then what we should see is this pet should now be following my character as like so, except it is not. Okay, we don't want to forget about setting attachment 0 to our attachment, and we do the same thing with the line orientation. We don't want to forget about setting those. Those are pretty important. Okay, so now if we hit play, then what we should see is this pet should now be following us as so, just like this. So it's not only following the direction of where the player is looking, but it's also constantly calculating its position to be behind the character and to the right of it slightly, just like so. And so that is how you create a pet follow script. And I hope that this example has helped you use AlignPosition and AlignOrientation for other use cases that you'd want to use inside of your Roblox game. Okay, so mover constraints are pretty cool, but now I want to get into some mechanical constraints that uses Roblox's physics to essentially create these mechanical connections between 2 or more assemblies. And some examples include ropes, welds, ball sockets, hinges, and stuff like that. But essentially, all you would need to do to create these constraints is you can do it through the same method that I've been showing by hitting the plus sign and inserting an attachment and whatever constraint you want to add. Or we can do this through the model tab as well. So what I'm going to do is insert 2 parts inside the workspace, just like this. And what I'm going to do is go to this tab called constraints with this create dropdown. And we have all of these different movers and mechanical constraints to work with. So let's say, for example, I wanted to use a rope. So what it's going to do is we can set where we want the attachment 0 to be, and then we can set where we want attachment 1 to be, which can be over here. And this is another way that we can create a constraint inside of our Roblox game. As you can see, it automatically created attachment 0 and attachment 1, and it created the provided constraint for us right here. So if I were to, let's say, move attachment 1 up here, and if I were to make this part anchored, then what's going to happen is if we hit run, then there should be a rope that's attaching these 2 assemblies together so that it creates this mechanical constraint like so. And we can do this with many other constraints as well, but for the sake of this tutorial guide, I'm only going to be showcasing a very few number of them. So I want to show you this simple ragdoll system that I created when you reset your character. My character is going to look like this, where instead of exploding into a million pieces like any typical Roblox game, instead what I'm doing is I'm using mechanical constraints, specifically ball sockets, to attach all of my 15 parts together rather than exploding it into a million pieces. So I'm going to be showing you what I did inside the script without making this like a step-by-step tutorial guide, otherwise this tutorial would be a little too long. But all that this script is doing inside of server script service is we're locating every single player that joins the game and every single character that joins the game, and we want to set this humanoid property called break joints on death to be false. And we want to do this so that the joints that are connecting all the parts together aren't going to fall apart when the player dies. So what we're doing here is when the character dies, we want to locate every single Motor 6 instance. And if you don't know what Motor 6 is, it's basically an object that allows parts that are connected to each other to move in an animatable way. And so we want to locate all of these Motor 6 objects inside the player because there's about like, I don't know, 14 or 15 of them. And we want to create attachments for each Motor 6. And we want to create what's called a ball socket constraint to have these attachments go hand in hand and have them be located within that specific region of the character. And so if you're still confused, literally the whole point of a ball socket constraint is to force two attachments to be in the exact same position while also allowing them to freely rotate however they want. So the position is constrained, but the rotation is not. And so that is basically what you need to know about ball socket constraints. Now you might be wondering why there's an if-else condition here with the neck specifically, and that's because we don't want to have the neck wobble around because our camera is attached to the player's head. And so it would have like this weird effect if we were to make it happen like that. So if I were to quickly demonstrate what this would look like, if I were to just have it so that we have a ball socket constraint in every single Motor 6, then what's going to happen is, yeah, look at that. My head is just rotating all around. We do not want that to be the case. So that's why we have a special edge case for the neck to have a weld constraint. So we're just simply attaching the head and the upper torso together without any special constraint using ball sockets. And so that is a really basic way to create a Ragdoll script when the player dies. And I hope that you learned a lot from just me analyzing this script for you. So for this last part of the episode, we're going to be creating a projectile system using physics calculations. So what I have going on down here is a tool. So if we equip this tool and I click anywhere in the world using my mouse, then what it's going to do is it's going to shoot a fireball from where the character is to the direction of where my mouse was when I clicked. And it's going to use physics to create this sort of arch motion that involves projectile motion to create this result. And that's what we're going to be doing inside of this episode. But I do want to give a disclaimer saying that we're not going to be focusing on anything related to hit detection or player damaging or VFX or even sound design. We're just going to be focusing on the physics calculations that are involved when creating this projectile motion effect. So with that being said, let's go ahead and create this projectile system. Okay, so to speed things up, I'm going to show you my setup for this projectile system just so that we can get into the server-side scripting aspect of it. So what I've done is I've created this projectile that has can collide turned off, and this is going to be stored inside of server storage so that we can use it every time we create a projectile. I added a tool to starter pack, and I made sure requires handle was turned off because we don't need a handle for this tool. And I just added one local script inside of here. So basically all this is doing is we want to get the player's mouse. We want to locate this remote event that I put called Fireball inside of replicated storage. And we want to get the mouse position of where the player clicked inside of the world. And we're simply just going to send this information to the server so that we can let the server create the projectile and make it move along that direction to where the mouse position was. So that is all I did for the setup. And now we can get into the server side of the scripting. And so basically what I have here is I have the remote event with on-server event. We have the player and the mouse position. And we have some variables here, speed, which tells us how fast do we want this projectile to move per stud. And we have this gravity multiplier and max distance, which basically tells us that if the projectile goes over the distance, then we just want to get rid of it. But I will explain more of this in detail later. So there's three important aspects here with the server-side code right here. So we have the setup, then we create the projectile, and then probably the most complicated part, which is updating the movement every single frame. And I'm going to go over each part as we type all this out. Now, I want you to imagine that this is our player, this is our projectile, and this is the motion that we want this projectile to achieve when we click our mouse. So we're going to start over here. Let's imagine that our player has clicked on their mouse and the mouse position is like somewhere over here. So this is where the projectile is going to initially start. And with properties like velocity, speed, and direction, we take all of them to determine where it starts and where it needs to go every step of the way as it continues to go further and further with respect to gravity. And we're going to be inching our way to create this projectile motion arch using run service so that it gets updated every single frame. And that is basically what we're going to be achieving here with this script that we're about to code up here. So going back to our script, we're going to set an origin point, which is going to be located on the character's humanoid root part. So we're going to say local origin equals player.character.humanoid root part.position, just like this. Now we need to be able to locate a direction of where this projectile should go based on the mouse position and the origin that we've just created over here. So what we're going to do is say local direction equals mouse position minus origin. So mouse position is a vector3 value, and we're just going to subtract it with its origin. So this basically gives us our direction, but it also gives us the distance with that direction. So we don't want the distance involved with our direction. So instead what we're going to do is wrap these in parentheses, and we're going to say dot unit, which basically gives us a length vector that just tells us the direction that we want. So this essentially tells us that we don't care about how long this difference is between the mouse position and the origin. We just want the direction as it is. So if I were to help paint this analogy for you, this is basically where the mouse position is, and this is where the origin position is. And if we subtract the two, it gives us a distance, but we don't want the distance. We just want a unit vector, which would be like, I don't know, 0, 1, 0, or 1, 0, 0, or 0, 0, 1. That's kind of the basic idea behind it. And so that's what we want to try and get with this direction. We just want the direction. We don't care about how long it is. And next thing that we would need to do is calculate the gravity involved, because in order for this to be a projectile motion, we need it so that every single time that we update the direction and distance, and also velocity in this case, we want to make sure that gravity is being affected where the projectile is in this motion. And we can do that by using the workspace's gravity property, which you can see down here by default is 196.2. So what we're going to do is say local gravity equals vector3.new, open and close parentheses. And what we're going to put inside of here is 0. And what we want is negative workspace.gravity. And then we want z to be 0. So basically what this is saying is we want to take the default gravity, which is 196.2, but we want the negative version of it because we want it to be affected by gravity going downward, not upward. And so we want to multiply this by the gravity multiplier, which I've specified up here to be 0.25. And the reason we have a multiplier is because this is what allows us to adjust how much the gravity is playing into effect when we shoot the projectile to go where it needs to go, if that makes sense. Next thing we're going to do is create our projectile. So we're going to say local projectile equals projectile object, which we declared up here in server storage. We're going to say colon, clone, open and close parentheses. We're going to set the parent of the projectile to the workspace. And before we do that, we need to position the projectile to where it should go initially when we create it, which is going to be located somewhere around the player's humanoid root part. So what we're going to do is say projectile.cframe equals cframe.new, and we want to specify where it starts and also where we want its orientation to be as well. So for the position, that's easy. It's just going to be the humanoid root part's position. Now for the orientation, we want to make sure that we have the origin plus the direction, which is what we calculated over here, so that we know where we want the projectile to be facing before we actually shoot it outward. So now down here, we want to update the movement for every single frame when we use run service. So first thing that we're going to do is define a few variables. First thing we're going to define is the velocity. We're going to set this equal to the direction times our speed constant that we created up here. Now, speed is measured in studs. So speed basically tells us that we want to travel 100 studs every single second for when we have this projectile motion. So if you don't know, studs is basically Roblox's unit of measurement. These are what studs look like. So in this case, these are 4 studs of measurement. But imagine that this is 100 of them that looks like this. So we want the projectile motion to go 100 studs per second. And that's basically what this is trying to stay here. So if you go back to our script, speed basically tells us that we want to travel 100 studs per second. That's basically what this means. So velocity is what tells us how much speed an object is going to travel in a certain direction. That's basically what velocity is. And so the next thing that we want to keep track of is the current position. So we're going to say local position equals origin, because that's where we're initially going to start. And then we're also going to calculate the total distance that this projectile has moved as well. So we're going to say local total distance equals 0. Now, this is where things start to get really tricky, and this is also the last part of calculating our projection. So I want you to pay close attention as we script this. So what we want to do is create a temporary connection. So we're going to say local connection, and then we're going to set connection to be equal to run service dot heartbeat. So we're going to run this every single frame per heartbeat. And then we're going to say connect function, open and close parentheses, enter. Now, there is one piece of information here that we would like to have, and that is the delta time. Okay, so going back to this diagram over here, we need to understand how we update the projectile's position and velocity when we're trying to calculate this projectile motion, since all of this is being done every single frame for a single second. And if you need a recap on how run service works and how we do run things on a frame by frame basis, let's take this as a reference. So typically most Roblox games run in 60 frames per second. I'm pretty sure you've heard of this term before. So 60 frames for every single second that runs. So if you want to figure out how fast a frame is, we simply just divide 1 by 60, and this will give us about 0.016. So every single frame is running for 0.016 seconds. And so this is happening about 60 times. And if we want to be able to go through this entire projectile motion in 1 second, we would have to make this projectile move about 4 studs every single frame until we can reach the end goal of, let's say, about 250 studs, because that's what we decided to set inside of our script. So when we do this, we need to update the next velocity while taking into consideration of gravity, and we also need to consider the next position that this projectile is going to move by taking a displacement average from the new velocity versus the old velocity, so that we get like an average, so that it creates like this smooth arch effect over here. And so we're basically doing this every step of the way. That's the whole idea behind this frame by frame structure. And now we're going to return back to the scripting part. So first, we're going to calculate the step velocity by saying local step velocity equals velocity plus our gravity that we created. And we're going to multiply this by delta time. And the reason we're multiplying it by delta time is because we're doing this every single frame so that we can create this smooth arch effect. Next thing we need to do is calculate our step displacement. So we're going to say local step displacement equals velocity plus step velocity. And we actually want to divide this by 2 because we want to get the average of the current velocity plus our step velocity. So we're going to divide this by 2. And at the very end here, we're just going to multiply it by delta time so that it's within Roblox's frame by frame loop. So once we've calculated these two, what we need to do is first update our current velocity variable to the new step velocity, just like this. So then we need to calculate the next position that this projectile is going to move at by using our position and step displacement. So what we're going to do is say local next position equals position, our current position, plus step displacement. And we're going to update the projectile's C-frame to reflect that new position. So we're going to say projectile.cframe equals cframe.new. We're going to throw in the next position as the position. And then for the orientation, we want to make sure that it's the next position plus the velocity.unit, because we want to have the direction for its orientation. Just like that. We're also going to be updating the position to be the next position. And just as a measure, we're also going to update our total distance to be whatever it is, plus the step displacement dot magnitude. And we want to make sure we get the magnitude of step displacement, which is basically the size difference between the initial velocity and the next velocity. And at the very end here, we're going to destroy the projectile if the total distance has reached the maximum distance of 250 studs. So let's say if we had the projectile and if it was to go above 250 studs, then we're just going to simply destroy that projectile. So I think this part's pretty self-explanatory. We're just going to say if total distance is greater than or equal to max distance, then we're going to destroy the projectile. So projectile.destroy. And because we have this connection here, we want to make sure that we disconnect it as well. So we're going to say connection : disconnect, open close parentheses, just like that. And so this should pretty much be our entire script. So if we hit test, I'm going to make sure to move projectile back into server storage. And now I'm going to hit play. So what we should see is if I press on my tool and if I were to click in a certain direction, then it's going to take that projectile and it's going to try and create this projectile motion arch to reach its end goal. And if it goes above 250 studs, then it's just going to simply destroy itself. Now, this is adjustable. So if we want to change the speed to, let's say, 250 studs per second, and we make the max distance 1000, then this projectile is going to move a lot faster if we do it like this. So as you can see, the projectile is moving a lot faster and we have a lot more range when it comes to how far it can go because we upscaled the max distance as well. And if we want to make this less of an arch motion, then we can make the gravity smaller so that there's less gravity involved when it comes to shooting our projectile. So I just reduced the gravity multiplier. And now if we were to shoot this, you can see that it's kind of going further along more than it needs to because there's less gravity being involved when we're shooting our projectile. And so that is how we can create our own customizable projectile system using the scripting that was involved here. Okay, so to recap everything, we want to use projectile motion to move a projectile from where it starts to where it ends using Roblox's run service to make this happen every single frame so that it creates a smooth arch. So when we start from where it begins at 0 seconds, we want to have this occur 60 times every single second because we want this to happen every single frame. And if we want to move 250 studs, then we have to move this projectile about 4 studs every single frame, just like so. And so the way we do this is, let's say our current position and our current velocity is over here. Let's just imagine that this is where it starts. So if we want to keep calculating what the next velocity and what the next position is going to be, we first need to calculate the step velocity. So we take its current velocity, which is over here, and we want to have it be affected by gravity, and using delta time, that's where it tells us where in this projectile we want this new velocity to be. And because we're constantly applying gravity to this velocity every single time as we update it, it's going to keep on going in this little motion over here. As you can see, this is indicated by velocity. It keeps on rotating until we eventually reach the end down here. So that is what is happening when we keep stepping our velocity. We constantly apply gravity to it to make it so that we can reach the next position. Now, speaking of position, we need to calculate the step displacement, which basically adds our velocity and our new velocity, and we average it out to get a distance between the two. So step displacement just tells us how far do we want the position of the projectile to the next one. That is all the step displacement is going to do. And so basically what ends up happening here is we update our new velocity to be the one that's right here. And we also update the next position to be the current position plus the step displacement. So it's now going to move over here instead of having it be over here. And so we keep repeating this process over and over and over again until we create this projectile arc to reach the end here. Once it reaches 250 studs, then we're just going to destroy this projectile. And so I hope with this explanation, you were able to grasp how projectile motion works and how we can use scripting to make physical calculations possible within our scripts. If you're wondering where these projectile motion calculations came from, you could just search up projectile motion formulas online, and you should be able to apply these formulas into your scripts if you're trying to make a physics calculation. I did not just pull these calculations out of nowhere, and there is meaning behind everything that you do when it comes to having the appropriate calculations for your Roblox game. And this does involve just kind of sitting down and understanding how all of these things work in order for you to understand why these formulas are applied and why does it matter to us for the systems that we are trying to create. There definitely is a learning curve when it comes to knowing how to apply physics inside of your Roblox game, but I hope that with this tutorial, you were able to get a little bit of exposure to how you can apply physics to your scripting. And I would say that if you have made it this far into the tutorial, then I would say that you are definitely up there when it comes to becoming a really great Roblox developer, because applying physics to your Roblox game is definitely not easy. So if you're willing to put in the time to be able to add these systems into your game by applying these complicated formulas into your code, then I think you're definitely on the right track to becoming a great Roblox developer. So with that being said, that's going to conclude today's episode. I would also like to give a shout out to all my Patreon members. I would like to thank them a lot for their continued support so that I can put out the videos that I enjoy putting out. Now, if you like the work that I put out on this channel and you would like to get access to my scripts, then I encourage you to check out my Patreon page for all the information related to that. But if you can't afford it, then no worries. There are other ways that you can support me with the videos that I put out by leaving a like on this video, and also by leaving a comment. I would like to know what you will decide to use physics for inside your Roblox game. So maybe a comment or two to describe what you're going to do with the knowledge that you've gained from this video would definitely help me a lot. I tend to look at all of my comments, at least for my most recent videos. So I would really like to know what you're going to do with this knowledge that I provided to you. And with that, this has been episode 36 of the Advanced Scripting Tutorial Guide talking about physics, and I will see you in the next one. Take care.